could hide that and hide this, and now we could start doing the class. Okay, so you're asking about the third problem on my exam. Not everybody's in my class, so I don't necessarily know if it's fair to take up their time explaining this, but I did try to make marks on the exams to try to give you sort of a nudge in the right way. It's the big idea in that problem was you were supposed to do a coordinate transformation into polar coordinates, because you know the direction, you know the acceleration. You can easily find the accelerations in the tangential direction and the normal direction, which fortunately in the problem are aligned with the x and the y direction, so that makes it just a little bit easier. And so I'm traveling down a road like this right here. I brake, therefore I have an acceleration in that direction. I'm going around a curve, so I have this acceleration. So I can find these values pretty easy, right there, right? And I already given this right there. So, but then I have a cop over here somewhere, radar gun pointing at me, and we want to find out this, so therefore this is the radial direction, and by convention, here's the theta direction. Are we good so far? Make sense? So this one right here, we could, if I wanted to, I could say that I had tangential and normal. I could go ET and EN. We could also just say it's I and J. You know, we have a choice. We do either one. It doesn't matter. We just know that that's a negative value here and this is a negative value here. You just need to write out the velocity equation and the acceleration equation in either terms, right? You could do it in the tangential direction if you wanted to. Right? That's supposed to be EN. Or you could do it into the rectangular. It doesn't matter. You would just, whatever you want to do with that, but then superimpose these ET, ER, sorry, ER, E theta, and probably, you know, a little bit of this depends on where you consider this angle. You know, you're going to have to, you have the dimensions here, so you could pick that as the angle, or you could pick that as the angle. So you just label the angle onto here, that one, and then you make the coordinate transformation grid into this. I'll do it like that right there. And probably go ER and E theta, and then, of course, whichever one that you did, whether it would be I and J here, or ET and EN, I gravitated to to writing it out this way. And then use this. Turn this into velocity in terms of ER and E theta. This is identical to like about 3 different problems. One example that we did in class, another example that was available as a video, several other problems. Right, and then you just run through once you get into the terms, once you have V in these terms right here, ER and this E theta, we recognize that that's R dot, this is R theta dot, so we're able to find R dot and theta dot, and then we do the same thing here. We don't actually need to do this one, that saves you some time. Here's the one that we want. Well, I'm sorry, right here. This right here is supposed to represent that we've transformed from whatever coordinate system, the acceleration that we had right here, we transformed it into ER and E theta, so we know that this one's equal to R theta double dot plus 2 R dot theta dot, which we just got up here. So we're able to find theta double dot. I know it's a fast explanation, but also just note, you have done this problem before. We have done this problem, and it also, a homework problem was that way. Does it look familiar? The fundamental thing that we're testing in this course is applying concepts, not memorizing problems. And that's the hazard, the thing we have to try to break, the habit we're trying to break. But it's been going on for 20 years, right? So it's not fair that we want to break it overnight. But we're trying to break the habit of looking down there. This was, you just have to imagine, use your imagination, how that is the same problem as that helicopter with the car. Do we have a helicopter with the car? Homework problem, or is that an example problem? Yeah, the helicopter with the car. This is the helicopter with the car. Just a little difference is that he's turning a corner, so there is a component going that way. So I wanted to do path coordinates problem, so that's why I added that in. So anyway, let's talk about recitation shit today. Stuff. No need to swear. Nah, I probably did. I'm gonna start swearing more. So this is week 5, right? I think so. And I think that's the PowerPoint, week 5. Well, that's weird. Where did that come up? Looks up. It's blank. I think it's just the computer being slow. There you go. Week 5 recitation. So what did we learn this week? We did classes 7 and 8. Class 7. Let's go up. Class 7 was the second part of Newton's second law, where we applied Newton's second law to path and polar coordinates. And then we class 8, which was yesterday, wasn't it? It was yesterday for some of us. It was yesterday. And that was the introduction to applying work energy to problems. So those are the type of problems I want to go over today. Boom. So here we are. And sure enough, yeah. So it's the second half of chapter 12, and then some of the beginning of chapter 13. And in terms of equation sheets, there's where it appears on the equation sheet right there. I think this one is updated. No, it still has an X in there. Yeah, but I am using U instead of W, so some progress there. So I'm going to have like a problem type requests. Here's ones that are posted on the. Oh, by the way, did I pass it around? I did pass one. Yeah, I was moving around. Okay. I moved it. All right, cool. You can just leave it over there. Somebody might show up. Maybe just shove it towards them. That's cool. So like the recitation website or Blackboard, we have like a couple examples here that might help us to try to almost said work through, but that would have been a pun, right? No more puns. We're not down with puns. All right. So any of these look appealing to you, or do you have a particular? Hey, can you do this kind of problem? Which one? This guy? Yeah. That guy? Okay. I even print them out. Thank you. Okay, so I don't have to read. But we need this camera right here. I gotta see if this camera is covering enough of the board so that people who would watch this video can see it, but not in your way, right? No, not here. Okay. Gotta double check this kind of thing. I tell you what, sometimes it feels like you're juggling and bouncing on one foot. I'm not complaining, I'm just saying. Yeah, they might be able to see that. Pretty kind of far away. Yeah, it's their own fault for not being here. I'm joking. I joke because I care. No, it's not true. I joke because I think I'm funny. My sister used to say, you think you're funny, but you're not. Yeah, maybe you agree. Blocks A and B shown in this figure have a mass of 10 kilograms and 100 kilograms respectively. Determine the distance B travels when it is released from rest to the point where its speed becomes 2 meters per second squared. Okay, it's a very small little place to sometimes I think I should go over here. Anyway, one thing that we know right away, right? Problem recognition. The dependent motion involved, right? It's pulleys. So we had to set up the dependent motion and see what the relationship between the velocities are going to be. Also, that's going to be the relationship between the position change. So we have to pay attention to that. We know that this is a work energy problem, but also because it's from that section, but also because of the nature of the problem. Like we have a velocity and we have a distance. So those are like clues that like this is a work energy problem, because work energy often deals with distances and velocities as opposed to dealing with forces and accelerations, right? Forces and accelerations, they look like Newton's second law. We could actually do this problem in Newton's second law. It's possible to do. Work energy might be, you could make the case it's a little easier. So set up the dependent motion problem first. If I can draw all of this stuff here in a small space. A lot of this is the drawings. There's a lot of drawing things involved here. All right, so this guy's up the top. This one goes around a pulley, which comes back down to that pulley, which comes up to this pulley, which goes down to this guy. So something along those lines, and this is B, and this is A. There's some colors involved. You stay there. All right, so little dependent motion thing. We'll set up a datum right there, and so we'll call this one SB. I think it's even already drawn on there, right? Yeah. We'll call this one SA. And if we take the length of this thing, we go 1, 2, 3, 4 times SB plus SA. And we can take the derivative of that and say 4 VB plus VA, and therefore VA equals, we could say negative 4 VB. I personally just avoid trying to use the signs for anything. Forget about the signs. Unless you had to, unless it's a complicated thing, don't let the signs fool you. We just know that they're, and it's not going to matter for work energy because both of the velocity is going to be squared, so their signs don't actually matter. One little trick here is we want to have the displacements as well, which we might be tempted to come back up to here, but we have an unknown length. But what we could do is we could say, well, these velocities, even if they're not average velocities, they're still dv dt, they're still dy dt, right? So we could just multiply by any increment of time, both of them, and it would become their displacements, right? So it doesn't hurt us to do that. So we could also say, well then, likewise, delta YA is equal to 4 times delta YB. Great. Now, make sure the thing is starting from rest. I think, yes, it's starting from rest. It's released from rest. So that's good information, right? So we have this whole thing set up, and I will urge you when writing out, you see it's a work energy problem, to start by writing KE1 plus PE1 plus U1 to 2 is equal to KE2 plus PE2. Now, I'm not 100% sure that Dr. Rico does this, but maybe, I think Dr. Orlov does. Yes, sir.
Is that a 4 in front of the delta?
Should be, yes. It's ugly, right? My finger's ugly enough too. Be aware that the textbook, I told my class, but we'll make the other classes might be using something else. This is done in the textbook. They go T1 plus big V1 plus, I think they use W, I can't remember or not. If you have the, they go T 2 plus V2. I have years ago decided that I don't like these symbols for the kinetic energy and the potential energy. So just be aware that those exist, and so that you're able to follow the textbook. And it is very common to call those, use those variables for the kinetic energy and the potential energy. But I think it's confusing because we use T for torque sometimes, we use T for tensions, we use V, the capital V versus a lowercase v. You can't really quite tell unless you make a kind of script kind of thing. And then W could be weight, right? So these variables get used too much. So this is also done in other books. So I like to make a list because that's the act of thinking my way through this thing, right? The writing of the list is part of the process of thinking and will help to maybe trigger an aha, right? And we go, as I'm thinking, I'm breaking the thing down, and then at some point I'm going to go, oh, I got it. Well, we start at the KE1 and think about, well, what is the what is the initial kinetic energy? Zero. Thank you. I just want some participation. And I think this is just me, you guys just sitting back and listening to me. Even if you don't answer, think. All right. Zero. Yes. Starts from rest. What about potential energy? Okay, so here is sort of a choice in here. Potential energy. Here's my approach. I like finding things that have zero potential energy and using them as their own reference. There are two particles in this problem. So this thing is, well, actually, we don't even know which way this is going down. But let me see. We don't know which way this is necessarily going, right? We might actually need, I think that 100 kilograms is going to win out, right? So there's like a 4-to-1 ratio thing coming on here in the pulleys. So I think B is going down. Are you with me? We might need to do some side calculation, double check that. But I think that B, even though he's got 4 cables in it, you know the tension's going to be constant, right? The tension in that cable is constant because these pulleys don't have any mass and they don't have any friction. So the tension has to be same everywhere. So this guy, he's got 4 cables keep pulling him up. This guy's only got 1 cable pulling him up. And this guy is 10 times larger than the other one. I think B is going down. So I think A is going up. So I think this would be a good place for the datum. Of A. So his potential energy at the first state, right? We're drawing this thing at the first state. Sometimes it's better to maybe make a little diagram of the thing, what happens later, right? This is going to be where it goes up later. You agree with that? And then this thing, we're going to exaggerate it, but this is where he ends up later. So I'm going to write this as the datum for A. And then down here, I'm going to have this as the datum for B. So this is going to be state 1 right here. Here's really state 2. I'm drawing them on top of each other. So for potential energy is state 1, 0 for this guy, but this guy has potential energy. And we will label from here are, well, I got to be careful with that right here because this is not a good place for me to label. So I almost want to reset maybe, or redraw. Maybe it would be better to redraw to avoid confusion. I am going to call from this position, which is not necessarily in line with that. It just was a coincidence, by the way. Maybe I should have purposely said that I can have an individual datum for each particle. This one just happens to look like it's in line with this. But I'm going to call this dimension right there, that's going to be its delta y. Delta yb. And I will call this dimension right here delta ya. Even though they're not drawn to scale. So the potential energy is really going to be my M, B, G, delta, Y, B. I'm looking at the solution here, and they decided to use those as work, right? So just be aware, at some point in the in the first part of the Beer-Johnston chapter 13, they decide, instead of referring to something as potential energy, they refer to gravity times the weight as a force, and they consider that as part of the work. But in my class, I decided, let's just go ahead and introduce potential energy in the first of the two work energy classes, instead of waiting as the book would have you do. So anyway, in this, this is the thing we were trying to find, right? We're trying to find the distance that B travels. So this is actually, the unknown that we want to place in there. But that's all the potential energies. And now in the work, we're going to consider that to be 0 in this case, because there's no external forces applied to the thing outside of gravity, but we're taking care of that with the potential energy. There's no friction to rob anything away. And then we have kinetic energy that's going to be happening at state 2. And we have to recognize that it's going to be 2 parts to it. Each particle, each box, has a kinetic energy. So we have 1/2 mb VB2 squared plus, I don't know why I decided to do B first, MA VA2 squared. And then lastly, we have potential energy 2. And that's going to be MA G delta Y A. And once again, I wish I brought my calculator. So we say, here, this is the thing we want to find. And they're asking us to find for B. Okay, so that's good. So B has 100 kilograms, 9.81, and delta YB, thing we want to find. This has 10 kilograms. Oh, sorry. I did B first. The speed they're saying is 2 meters per second. And now we also need A. It's 10. Now we need its speed. What is its speed when this thing is 2? This one's going to be 4 times the speed, right? So 4, 2, and squared. So people can help me by running their calculators at the same time as me, because I'm slow and stupid sometimes, some days. So 64. Let's see. And I like to do this sometimes. I think I got that right, that's 320. Let's see what that is. So that'd be 4 times, so that'd be 200, right? Anybody want to say yes? Come on, make me feel bad. 200. So did I get the right answer? 520. And these are units of Newton meters if you want to know, or even if you don't. And then down here, that's going to be 10 times 9.81. But now we want delta Y. We want delta YB. So we can substitute in here. We're going to see 4 times delta YB. 981 delta YB. And do that with do 40 times 9.1. $392.4 delta YB. All right, so we stick all those back up into this equation that we wrote at the top. And what do we get? See, kinetic energy is 0 plus the potential energy 981 delta YB plus the work is 0. I don't know, we might be off of camera now. We have 520, and then we have plus 392.4 delta YB. So we're going to bring him over to the side so we can subtract out 981. So we end up, and then, so we can take a 520 and divide that 520 by, what we end up is like 588.6, like that there. So we're saying that the amount of change in YB is going to be 0.8835 meters. And yeah, got it right. Woohoo! And we might want to say that, you know, to be complete here, because we want to fully communicate that that was down. Does that make sense what we did all the way through?
Right. Yeah, I just have a question. VA is equal to 4 VB. So wouldn't you have divided 2 by 4 instead of multiplying it?
Okay, maybe I did it wrong. Where?
What is it? Yeah.
That's 4 times 2, right?
Yeah.
Because that's Y, that's VA.
Yeah, but VA is equal to 4 VB.
Yeah.
So wouldn't you divide VA by 4 to get if?
Well, VB is 2, right?
Yeah.
So we're just plugging 2 into here. I mean, into there.
Okay, yeah, but to get the
So
equal
we-
amount for VA, wouldn't you divide it by 4 or not?
We're going to multiply because we're trying to find VA, or we're trying to put VA into here, right?
Yeah.
Okay.
Okay.
So VA is equal to 4 times VB,
Yep.
and VB is 2. So this is VA 4 times is 8, I guess.
Oh, okay. So you're
Yeah,
saying.
yeah. Okay, cool.
Pretty much.
No, I totally understand. The organization of it, the way it looks, and that kind of thing, it would be very easy to get flipped up. We got another request, another type of request, or?
Another question. What, can you remind me why work is 0?
Okay, so work is 0 because, all right, depends who did you have for your faculty? Don't tell it's me, because I'm sure you're not in my class, right?
No.
Okay. I did that the other day. I'm in your class. Okay. Okay, so in your class, is your professor using potential energy? Yeah.
Yeah.
Yes, they are. Okay, cool.
Yeah.
So I'm just asking because some people go in the first half of the chapter or the first section of the chapter when it comes to work energy, they don't introduce the idea of potential energy, and they say it's like the work work done by the weight, right? So it's the weight times the distance it moves, and it's confusing, I think. Much easier to potential energy. But in this case, the work is 0 because there's nothing outside. I always often think of this and try to associate with external work, right? There's something external to the things that's like either putting more energy into it or stealing energy away. And there's nothing there that's doing it. So this ends up becoming a conservation of energy problem. I don't know if I explained it adequately.
I have a conceptual question.
Okay.
Since it's accelerating due to gravity.
I thought we were gonna go through that problem in a second.
How is the tension constant? It doesn't affect the tension?
Well, tension's constant because acceleration's constant because of all the forces are constant, right? None of the forces involved, which are all really due to weight.
Yeah.
All of the forces in this are due to the heaviness of the blocks. Those never change, right?
Yeah.
Therefore, acceleration never changes. And therefore, if you were to do a free body diagram of either of the blocks, right? Whether it be this one right here, which would give you 4 forces right there, and the weights, right? And you would take a look at the IBD of this thing. So you get an FBD, IBD. You would see over here, it's like, okay, well, there's acceleration of V, right? These forces never change, so this acceleration never changes. So that tension has to be the same.
The tension doesn't increase because of the...
No.
Okay.
You could also, what you could do is you could draw a free body diagram of the pulley itself, right? And just take a look at this thing and take a look up there and go, okay, are the forces, of course I'm not supposed to draw the ground. There's something hanging right there, and there's no reason for that, for there to be a difference between those tensions. Not at this point. When we start to give this thing a mass, then we actually have to, you know, I should have left room to do the IBD of this as well, and you see the IBD is not moving, right? Nothing moves, so the tension, there's no reason for the tension to ever change. It's a good question because it's there's a certain amount of gut feel that could make you lead you to feel like yeah that tension's got to change. That tension's got to change. So you have to kind of like have that little thought. You know, need to ask, but also have that little thought experiment there to try to or work your way through to try to convince yourself that of something, especially when your gut tells you one thing and it turns out it's not true. That's like the reorganizing of your brain, and some of what gets done in this course and in many courses. All right, anybody have a suggestion for another problem?
Can you do one from the homework?
We'll do one like the ones from the homework. Did you have one in mind?
Yeah, number 3.
Okay, so that's actually a pretty difficult problem. I had a hint that I put in there. I did put the hint in. We're talking about the one that's where I gave the hint that you use a quadratic equation. Is that the one that I have? Is that the one we're talking about?
Is that homework 7 or homework 8?
Yeah, we're talking homework 7 or homework 8.
8.
Homework 8?
You put the hint underneath the question.
I think so, yeah. Okay. It's a challenging question, so you have an opportunity for an oh yeah moment. So like, let's see if I have one like that at my disposal. Not exactly, but I could pick one out of the book that's similar. All right. Where's my time looking? I just got a guitar. It just arrived at home, my wife told me, so it's like really tough to like sitting right here. Right? I got a new guitar. It's a lucite, right? So it's clear and it's got lights inside it. Isn't that stupid? I'm gonna look amazing. If only I could play guitar.
My birthday is coming soon.
Your birthday's coming soon?
Yeah.
So happy birthday to both of us. Okay, so sample problem 13.3. It's very, very close. The only problem is it's still using word. No, they don't have. They already know the displacement. That's the problem there. They already know the displacement.
How about you use the same problem just with different numbers?
That's a good idea. Why didn't I think of that? Here we go. Conservation of energy. We need the ones with springs in it. Not enough ones with springs in them. Here's ones where they're going around the world and they're making up things, and they want to impulse momentum. All right, so I'm not finding the spring. I might have to invent one. I've seen plenty of problems like this before in the past. It's just a really good problem. That's what the problem is. The problem is it's a really good problem. All right, so without having a problem in front of us, I remember a problem, must be from another book. Sure. Must be from another book, where we have this block. And he's sliding down, and he's got springs like this right here. This isn't the homework problem, is it? Is this the same one as the homework problem?
Yeah, if you want, I can verify.
Is it the same one as homework problem? I can't remember. Don't try to trick me. So anyway, we want to find out how far that thing is going to compress.
But nonetheless, you're doing it the other way.
Is it flipped over? What does it look like?
Is it a test?
Is this the same problem?
The one that you
Yeah, no, this is a different one. All right, cool. So the thing we want to do is, let's say the thing is moving at V1 equal, and let's say that this thing is 10 kilograms, and the total spring constant right here is equal to, I'm going to make it something small. I'm going to make it 5 newtons per meter. I hope that's small enough. We'll see. And then we have a coefficient of friction of, let's make it something small, 0.1. And this velocity, let's make it 10 meters per second. And let's say that distance to right here, I remember this particular problem being, there's a little bit of complication to it, so I hope it's not going to drive you nuts. But when you have something complicated, really what you need to do is just methodically go through it. Don't be overwhelmed by all the complications in looking at this. We'll make it just a little easier by making this 30 degrees and make this distance, I meant to draw the distance right into there. Let's make this 10 meters. And our goal is to find how much, when this box gets down to this next level. All right, let's draw. I'm going to draw the box in there. We're going to say the box is going to come down somewhere into there, right? And we want to find our goal. Find this amount of, let's call it a delta S. Right? Does that make sense? It's going to hit, it's going to slide all the way down there. It's going to hit, and then it's going to start bouncing back up. We probably won't finish this problem all the way through with the numbers, but we will definitely see why there's complication, right, as part of the thing. So our first thing to do is to write out KE1 plus PE1 plus U1 to 2 is equal to KE2 plus PE2. And then start them out. So KE1 is 1/2 mv squared, V1 squared, or 1/2 10 kilograms times 10 meters per second squared. So whatever that works out to be. It's like 500, is that right? No. You at? Yeah, it should be 500, right? We all agree? You don't care. You're just dazzled by my brilliance and how I'm able to just soft, I can tap, I can entertain you, play my guitar for, you know how many guitars I have now?
You have 3? Well,
I don't know. It's somewhere in the 40 range. I have about 40 guitars. And a very tolerant wife, you know, I brought her up. Right? I told her she could take the guitar out and play it, and she laughed. I did buy her a guitar once.
Can I take one of your guitars?
Was that? Are you asking if what?
If I could take one?
You want one?
Yeah.
That's really nice of you to offer to take one. Right. So we want to find a datum. That's so. One difficulty that we're going to have right here is that's the lowest point this thing is going to go to, right? So we would want to measure right here. This is going to be the delta y of that box. But part of that is going to be this 10, but it's also going to be plus that delta s right in there. What a pain. Is that a pain? I agree, it's a pain. But, so what? You just do it, right? That's also an engineering principle. It's tough to do. Just do it. Go tell your boss this. Just tell how hard your job is. You know what my boss would say? That's why we pay you. To do the thing, to do the hard things. If it was easy, anybody could do it. That's why we have liberal arts majors, because they can't do it, right? And they're going to get paid accordingly. Sorry, liberal arts majors. So we have mg delta y, so that's going to be 10, 9.81, and then the delta y, maybe we'll write it over here, over to the side. Delta y is going to be equal to 10 plus delta s times the sine of 30, right? I don't know why I wrote it over the side. I could write it right over there, right? Oh. 10 plus delta s times the sine 30. If I want, I could go ahead and find what this is going to be right here. Right? So I'm going to get 10 times 10, 100, 981, and times the sine of 30 should be 0.5, right? Sure. So 981 times that, we have 490.5, and then we're also going to have 98.1 times 0.5. Cool. So that's going to have just 49.05. Tell me if I did any math wrong, please. Anyone keeping me honest? I don't know. I'm just winging it. Just winging it. Improv, baby. I don't really memorize songs very well. So all my guitar solos are improvisations, except for a few, and I always screw those up. Okay. So now we do the work. What kind of work is happening on this thing?
The spring.
We consider the spring to be potential energy, but you're not wrong, because that's actually, some folks do consider it. But we have this ugly little guy right there causing trouble. Friction, yeah. So maybe we don't actually have to do an IBD onto this thing, although but we do need an FBD to organize our brains, so we could, at least my little wee little brain right there. We have mg. Here's our x prime and our y prime. We got a normal force and a friction force. Might as well complete the thing and draw it like there, right? But the whole reason I'm doing this is just to stay organized and say sum of the forces is equal to mass times acceleration. Let's say that some of the forces in the y prime direction, and fortunately it's going to be 0 in the y prime direction because it ain't going anywhere that way. So we go Fn minus mg times cosine, right? So Fn is going to be 10 times 9.81 times cosine of 30 . Yeah, I lost cosine. I lost the time too. What time is it? I can't read that. 15 till? 10 times 9. It's right here on my phone, you dummy. Right there. I'm staring right at it. Staring right at it. Right there. I could have just looked right there. So old, I want to look at the clock. That's just sad. 84.96 maybe. And then our friction is going to be mu Fn, or 0.1 times that, or 8.496 newtons. So we have negative friction force times the total distance that the thing moves, which is once again going to be, let's say delta S total, which is going to be negative 8.496 times 10 plus delta S, right? Because it's going to move the entire 10, but then it's going to hit this box and it's going to keep on moving this extra little bit right here, that extra delta S. So I said this is delta S total, because it's the total thing that goes, so it's both of those things. So we have negative 84.96 and also negative 8.496 delta S. Orange, terrible. Orange is terrible. Not a good color. I'll do blue. All right, so kinetic energy 2. Oh, thank goodness. It's 0, yeah, because it's going to pause. That's we want to find the maximum on displacement, so it's going to momentarily pause before it starts to go back up the slope up there. And then last one is going to be potential energy 2. And whereas we chose this to be the datum right here, that's well and good, but the spring's going to have potential energy, so it's going to have 1/2 K del squared, del 2. One thing I didn't do that's in some books, one of the sources, sometimes they'll put a wire. They'll connect a wire right here and say that this spring is already compressed before this thing hit it. And then that would mean that this thing would have some potential energy up here. I didn't need to make it any more complicated than it already was, but just saying, it happens. So right here, we have 1/2, the K is only 5, and this delta, this del, is actually this delta S, right? That's the amount that the spring is going to be compressed. So that becomes delta S squared, or 2.5 delta S squared. So now add them all up. Put them all back into this equation right here. And say we have 500 The next one over, we have 490.5 plus 49.05 delta S minus 84.96 minus 8.496. All right, it's going to be equal to 2.5 delta S squared. So collect some stuff. 2.5 delta S squared. And then let's see, the ones with a delta S in front. Did I miss one with a delta S in front? I did, didn't I? We have this one. Oh, there you go. There you go, right? So let's see, that's a negative one, that's a positive one, but so this is going to end up being a negative number here because we're going to bring them over to the right-hand side. So we take that 49.05 and we subtract out. And so it should be 40.55 delta S. And then take a look at the other. We're going to have, let's see, 990.5 and subtract out 84.96. Did I say that right? 990.5 and subtract out 84.96. We're going to have a negative. So this is going to be a negative 905.5 if I did it right. And there's all kinds of opportunities for me to have screwed this up somewhere and made a math error, but hopefully you get the idea. So now you want to find delta S. We take the quadratic equation, which I don't think students do anymore, right? No, you just use your root solver. Well, there's something to be said for a good old quadratic equation. So delta S is going to be equal to negative of this, which is negative 40.55, plus or minus the square root of that 40.55 squared, minus 4 times A, which is 2.5, C, which is a negative 905.5. And thank goodness that's negative, because we're not going to have to worry about it possibly going into, this is the reason why this is worth it. If you're getting like screwy imaginary numbers, now you can backtrack and figure out why you're getting imaginary numbers, complex numbers, because we don't like complex numbers. We're not electrical engineers. They like them a lot. Unfortunately, we start to like them again in control circuits, controls, and like in automation, that kind of thing. Yeah. Trust me. It's all about the, oh boy, I can't even remember what the Laplace transforms. Remember the Laplace transforms? You ever use the Laplace transforms? It's kind of elegant. I don't know. Good way to do differential equations. All right, so anyway, then on the bottom, 2a, 2 times 2.5. And we might get one of these numbers might be negative. That don't make no sense. So, or there could be 2. Well, it's gonna, if you got 2, it's probably gonna be, that's gonna be the smaller of the 2. We have to write, I think in this case, one of them is gonna be negative. So, anybody already found the roots for me? So I don't have to do this? You're gonna make me do it, aren't you? This is how you're torturing me. It's almost as bad as having a guitar waiting for you at home and you have to go like make up a dynamics problem and look like a moron in front of a bunch of 20-year-olds. Actually, some of you are probably older than that, right? Or maybe younger. Or maybe you're just gonna ignore me. Oh, look at that! I just hit the frickin' number. My stupid phone likes to jump, so I have to do it all over again. You son of a... Shouldn't complain though. Life's good. I'm gonna hit the square root now. Boom. Okay. So this is all of 103.4. All right. So yeah. So this is going to be positive. So if we took the negative of this, this would turn this whole thing negative. So that doesn't make any sense. So we will add the two together. So I'll add 103.4 to 40.55. Add them, and then divide by 2, and then divide by 2.5. And we get a ridiculous number. So this is why I make I spend way too much time making problems, because that would be really huge. That wouldn't make any damn sense. So you got to pick the values, or I could have screwed something up somewhere. There's a good chance of that. But when you just pick random numbers, this is what happens. Like that spring, he just ain't enough. Not to mention 10 meters, that's a pretty far distance for this thing. It's going to be, and it's with a low friction. One of the side benefits of approaching it in the way that I've shown right here, doing this, and then going down through this process, and then writing them out like this right here, is when I get a stupid thing, as this is a stupid thing, I can start to work backwards and go, okay, well, what is the thing that's driving this? Okay, well, I can see this thing has a lot of energy in the beginning, right? That's a lot of energy. The thing is smoking at 10 meters per second. This right here, it's got a lot of potential energy, so those things are driving. I can also see, if I get like a weird number right here, that I might have made the spring too much. Right? So if if this became negative right in here, some of this right here, see that but also this guy right here is actually helping me so that this doesn't become negative. You can kind of see what I'm referring to though. It's the thought process of self-diagnosing, figuring out where you went wrong. Most of the times when I would calculate something, I'd get it wrong the first time. Right? And then I would go, well, what the, be pondering and on the lookout, like, where did I screw this thing up? So in a lot of engineering, I try to figure out if I can find multiple ways to solve the same problem. Sometimes making simplifying assumptions if it gets too hard to do, just so I can have this rational check, right? If you can calculate something, I've said this many times, if you can calculate something 2 different ways, calculate them 2 different ways. If you do 3 different ways, calculate them 3 different ways. 4 different ways, 5, that's just crazy, that's too many. But it was funny, by the way, it was hilarious. The delivery was just about right. But yeah, do it, and then force yourself to reconcile those. But that's for another time. I'm just saying, as a real engineer, that's how I approach problems, right? And then so setting it up in a way that you could self-diagnose and figure out, like, where did I go wrong? Where did I go wrong? Because we have that opportunity in the method that we're using for calculating the homework. We're going to be frustratingly not get the right number, and then see what the solution is and go, okay, I see where I'm supposed to go. And then you still might not get the right number, but if you really want it, then you go, search, go backtrack, see where it might have gone wrong, and then try to have that feeling of satisfaction when you're able to get the number. That's what I'm hoping for, at least. I'd also mention to you that there has been problems where people are entering the answer with 4 sig figs and getting told they're wrong. I think I set it to 3. Maybe I need to talk to Dr. Orlip and Dr. Arico and change that setting, but it's a setting in the system that I just, set it to 3 sig figs. The other option is like how many decimal places, but there wasn't really a way to set it. I guess I could just set it to a lot of sig figs, and then you're just off by 2%. Within the 2% you'll be fine. But anyway, it hates you if you put in 4 sig figs. I apologize. And I've also set it, I think, this time, I'm not sure, I set it so there's really only like 4 variations. I shouldn't tell you that, but I guess I should. So they're like, you'll eventually get the same numbers. You could just keep trying, right? So you get somebody to do it for you, you get the value of what theirs was, and you just try it 4 times until you get their values, and then just put the value in, boom, you're done. Yeah, that's the way to cheat. Okay.
What happened if we guessed and numerically we got the answer?
You know, I love hypotheticals. I don't know what would happen.
Yeah, you're supposed to turn in the written work, so that was the answer to that one.
Hello.
Hello, I was gonna check out the.
Oh.
Yeah.